Hello students. In last video we have seen that how to find incidence and adjacency matrix of the given graph. In this video we will see one example of incidence and adjacency matrix of the graph, and next we will proceed to the next point. First example, write incidence and adjacency matrix of the following graph. First, adjacency matrix of this graph, adjacency matrix. Suppose this graph is G graph, so adjacency matrix means A of G is equal to, here you can see that V1, V2, V3, V4 are the four number of vertex. So first write down the vertex column wise and row wise. First row wise V1, V2, V3, V4. Next V1, V2, V3, V4. First vertex V1 is adjacent to V2 and V4. So V2, V4 put 1, other entries become 0. Next vertex V2, V2 is adjacent to V1, V4 and V3. V1, V3, V4. And next V3, V3 is adjacent to V2, V4. V2, V4 and V4 is adjacent to V1, V2, V3. Also V4 has a loop, so put V4 as 1 and next V1, V2, V3. Because V4 is adjacent to V1, V2, V3, also this loop is considered as 1 and other entries become 0. So you can see that this matrix is symmetric matrix. First row, first column, second row, second column, third row, third column, and last row, last column. So this matrix is symmetric matrix. And next, incidence matrix. Incidence matrix I of G is equal to, first row wise write down the edges E1, E2, E3, E4, E5, E6. Total number of edges are nothing but D6. So E1, E2, E3, E4, E5, E6. And here write down the vertex V1, V2, V3, V4. E1, E4 adjacent to, incident on V1. So write down E1, E4, 1, 1. Next V2, E1, E2, E3 are incident on V2. E1, E2, E3. Other entries become 0. Here also 0. On V3, E2 and E5 are incident. So E2, E5. Other entries become 0. On V4, E4, E3, E5 and E6 are incident on V4. For E6, this is the loop, so consider as 2. Write down E3, 1, E4, 1, E5, 1 and for E6, 2. Because in the incident matrix we considered loop as 2. Other entries 0. So this is the incidence matrix and this is the adjacency matrix. For this, first you have to know how to find adjacency matrix and incidence matrix. This will be shown in the last video. Next point, some important graphs. First graph is null graph, means trivial graph. A graph with n vertices without edges is called as null graph. Notation n suffix small n is equal to null graph with n vertices. For example, n1 first vertex, because n1 contains only one vertex without edges. n2 means null graph with two vertex. This is the two vertex without edges. So this is the null graph with two vertex. n3 is first vertex, second vertex, third vertex. So this is the null graph of three vertex. You can name it as v1, v2, v3, here v1, v2, here v1, or others. Second important graph is complete graph. Complete graph means a simple graph G is called a complete graph if there is an edge between every pair of vertices. Here in this definition, graph G must be a simple graph. Simple graph means a graph without loop and parallel edges. It's called a complete graph if there is an edge between every pair of vertices. Notation k suffix n means complete graph on n vertices. For example, k1. Here k1 means complete graph on one vertex. So this is the one vertex, and here no choice of to giving the edge. So this is the single vertex without edges. Second, k2 means complete graph with two vertex. These are the two vertex and only one pair of vertices, means these two vertex mix a pair. So here we give the edge between these two vertex. Now you can write down the k3. So first put three vertex and give the edges in every pair of vertices. This is the one pair, this is the one pair, this is also one pair. So this is the complete graph. For k4, put four vertex and gives the edge between every pair of vertices. This is the one pair, one pair, one pair. Also this one pair already edge given. This is the one pair, this is the one pair. For this pair already given edge. So remaining this. So this is the complete graph on four vertices. Next, properties of complete graph of n vertices. First, each vertex has degree n minus 1. You can see that for k4, 4 number of vertex and each vertex has degree 3, means n is equal to 4. Each vertex has degree n minus 1, means 4 minus 1 is equal to 3. Here 1, 2, 3 degree of this vertex, also degree of this vertex also 3. And next, number of edges equal to n into n minus 1 upon 2. Here total number of edges 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 means n into n minus 1 upon 2 total number of vertices, total number of edges. N is equal to 4. 4 into 4 minus 1 upon 2 is equal to 4 into 3 upon 2. 2 1s are 2, 2 2s are 4 is equal to 6. Total number of edges nothing but the 6 for k4. So properties of complete graph, number of edges equal to n into n minus 1 upon 2. Next example, find the smallest integer n such that kn means complete graph on n vertices has at least 600 edges. So to find the smallest integer n such that, first of all we know that total number of edges for the complete graph is nothing but the n into n minus 1 upon 2. And kn has at least 600 edges, means it contains 600 or more than 600 edges. First, for the solution, complete graph on n vertices has n into n minus 1 upon 2 edges. But the graph requires at least 600 edges. 600 edges. That means Total number of edges of complete graph are nothing but the n into n minus 1 upon 2. It contains 600 or more than 600, means n into n minus 1 upon 2 greater equal 600. To take here means 1000 and 1200. If we put here n is equal to 35, sorry, n minus 1, so n minus 1 is equal to 34, and 35 into 34 we get 190, which is not greater equal this number. So if we put n is equal to 36, n minus 1 become 35. 36 into 35 means here we put value n and n minus 1. We get 36 into 35 is equal to 1260, which is greater equal 1200. So n must be 36. Therefore n is equal to 36. Here you can't take 37, 38 because here in this example we want to find smallest integer such that n has at least 600 edges. So n is equal to 36 is the smallest integer n. Therefore number of vertices of such a required graph is equal to n is equal to 36. Now here we stop.